Hello, ladies and gentlemen. We're going to get started for our session, and the first speaker is going to be Emily Sarneso, and she's going to talk about finding a needle in a PCAP. She currently is with SEI CERT, and she is the lead developer of the YAF and Super Mediator. And so I hope you enjoy her discussion.
Hello, I'm sorry to pull you away from the nachos out there, but I'm going to pull you away also from some graph analysis and math today to talk about YAF. That's what I think. It was going, whew. And something that we don't talk about a lot at FloCon, which is PCAP analysis. And I'm going to talk about flow analysis as well, but often, let's go back. Often when we talk to organizations, they have a big issue with their PCAP solutions. Why do we need full PCAP capture? Well, if you talk to anybody here, they would probably say, you don't need full packet capture. I mean, we're at a flow conference, right? But there's usually somebody in your organization that says, yes, we need it. But what do you do with it? You let it sit there, right, until somebody says, oh, I need something. Well, how do you get anything out of that much data? So I'm also going to talk about some of the PCAP features that have been in YAF for a while. We've revamped them a little bit, made them more efficient. And then I'm also going to show some analysis capabilities of some of the tools that I write, YAF and Super Mediator, and then also a tool that CERT writes, which is called Silk, which I'm sure you guys are aware of. So what are some challenges with PCAP? Obviously, volume is the biggest one. I started up our traffic generators in our DTE lab, which Dwight talked about earlier. And in just 1 hour, I collected 1.7 terabytes of data. That's a lot, right? And so if we're lucky, we can retain PCAP data for maybe days, maybe a week, a month, might be stretching it. Another issue is that data is stored on sensors. And a lot of times the analysts don't have access to the sensors. It often requires some administrator intervention to go get that PCAP data. Once we collect that PCAP data, we don't typically move it off of the sensor. So any queries that we make on that PCAP data have to be efficient because we don't want to mess with our flow collection or packet collection. Also, there are not a ton of tools to do PCAP analysis. You have your standard ones like TCP dump or T-Shark. How do we index that PCAP? Well, it's usually if we're doing some kind of rolling PCAP dump, we're time stamping the files and we're rolling those files over every 5 minutes, 10 minutes, or based on some type of file size. When we process the data, we can use things like BPF filters to say, I want data to this port from this port or for this particular IP. We can use GUI tools like NetWitness or Wireshark. NetWitness if you have a lot of money, Wireshark if you don't. But I don't know if you've ever tried to open up a large PCAP file in Wireshark. You can't do it. It just says, no thank you, I can't do this. So you have to find a way to slice up that PCAP file so you can. I've read that you can also use Splunk to store your PCAP headers. I've never seen anybody try this, but you also need a decent amount of money to use Splunk. Some other ones, CapLoader, they advertise that they can open an 85 gigabyte file in 1 hour and 47 minutes. I don't know that that's really what my IT department wants to do. Say, can you look at this particular hour of data and get back to me in 2 hours, when you can finally load that thing up. Cisco has a similar product called Cisco Compressed PCAP Packet Indexing Program, CPP-IP, which will index packets based on the number packet in the file or time. And I really don't know if the packet I'm looking for is the 100th packet in the file. how would I even know that? Time, of course, is a good way to index things, but you can only get down to the second, and we know that there can be a lot of packets in one particular second. So I want to talk about some PCAP features in YAF that people don't know about. A few years ago, I talked about some of the deep packet inspection features in YAF, and while those are still useful and people are finally starting to turn some of that stuff on, I added some features in YAF a while back that can do a lot of PCAP analysis. So one of the interesting ones is rolling PCAP dump. So it basically can do what TCP dump does, which is just capture packets and write them to disk. But also what it does is it creates what I call a PCAP meta file, which is one line for each flow in the PCAP file. And the way we identify a flow is similar to how Rachel and Eric do it with the 5-tuple, a hash of the 5-tuple, and the start time. So for each flow in the PCAP file, it will write one line in that meta file. It will write the flow key hash, which is a 32-bit hash of the 5-tuple in the VLAN, really 6-tuple, the start time in milliseconds, and then the file that flow is contained in. And so we have other tools that come with YAF that can run through quickly and identify where that flow is in the PCAP files. We can also index a PCAP file. So a lot of times in forensics investigations, we have a large pile of PCAP. And so how do we even start? So we can index that PCAP file using the same method with the flow key hash and the start time. And then we also have a feature called PCAP per flow, which for any particular PCAP file, it will create a PCAP file for each individual flow in the file. So you might not want to do this over a 2 gig file. You can have upwards of 50,000 flows in that file, but you can use that with BPF filters if you can manage to write a good one and break that up into smaller files. So the way I'm going to talk about some of the PCAP analysis tools is to go into some analysis I did on the Ghost remote access Trojan. And I'm not an analyst. I develop YAF, supermediator, and fixed buff, so I'm going to do some basic Silk queries. And so if you're not familiar with Silk, I think you should still be able to follow what I did here. So what is Ghost? I'm not going to go too much into Ghost. I just don't have enough time, but you can Google and find out enough about it. But basically, it's a remote access Trojan. The source code is free. It's easy to modify. And it has a distinctive network signature, which I thought, great, I write network monitoring tools. I should be able to find Ghost pretty easily. So you can see the 13-byte header is typically sent in the clear. Well, it's always sent in the clear. So the first 5 bytes are the signature, what some people call the magic word, which by default, if you don't modify the source code at all, is the title of this slide, which is Ghost. The next 4 bytes are the compressed length of the entire packet, and then the following 4 bytes is the uncompressed length of the packet. Ghost usually uses the zlib compression library. There's no other obfuscation or encryption used, and often they'll have the zlib header as the following 2 bytes, and then some variable size data after that. So what did I do here? Well, at CERT we have a malware team, and they collect malware samples. And we have some really smart people at CERT that go through these malware samples, and they identify similarities in the malware variants. And they classify malware into known categories. So Ghost is one of our known types of malware. And when they run the malware in their lab, they turn on TCP dump and capture any network traffic that the malware may produce. And so we had 29,000 PCAP samples, only about 15 gig. It's nothing huge, but a lot of PCAP files. And so what did I do? I used YAF to produce some flow, some DPI data, and what I use are what we call YAF signatures, which you might not be aware of, but I'll go into that. So what was my tool setup here? All my PCAPs were stored in a file directory. I started up FloCap, which if you're not familiar with Silk, takes IPFix data and turns it into Silk flows. I use a tool called SuperMediator, which I'll explain a little bit more, but basically it takes IPFix data and it'll write the data that Silk doesn't collect. So any depacket inspection data, any advanced flow statistics, that kind of thing, to CSV files. And then I also ran YAF over every single file in that PCAP directory. And some things that you might not be familiar with in YAF are the DPI features, the advanced flow statistics, which are things that I'll explain in a few slides. And then I cheated a little bit here. I used the observation domain, which the observation domain is a 32-bit identifier in the IPFix header. And I used that to say, for each PCAP file, got an individual observation domain. So this was nice because I could quickly go back and figure out where the flow came from. So if the flow had a observation domain of 67, I know, okay, it's the 67th PCAP in the list. So my initial results, and this is before I knew anything about Ghost. I didn't Google Ghost. I just thought, oh, maybe I can find something real quick in the flow data and be, yes, I did this. So I don't know a lot of Silk queries, to be honest. And if I have to do any real flow analysis, I walked down the hall and I said, Mark, like, how do I do this in Silk? And usually scowls at me, but then tells me the answer. But the one flow, or the one Silk query I do know is how to bin things by application label. Application label in YAF is just a way to identify which application protocol that the flow may have been using. And we use the well-known port as the application label. So I did my RW stats query, and it didn't really provide me anything useful. I had a lot of unidentified flows, a lot of web traffic, NetBIOS, some DNS stuff. So I was like, what do I do now? Well, I went to my friend Google. I said, Google, do you know anything about Ghost? And of course, it brought up a lot of reports. And the one that I found first was the Norman ASA 2012 report, which identifies 85 Ghost variants. And the way that it did that was by that 5-byte magic word, which is the first 5 bytes in the payload. So I said, okay, I wonder how many of the variants are represented in our malware catalog. So what I used YAF signatures, which is basically a way to give a regular expression and execute that against the payload of the flow data. And I gave each one of the variants the Norman report identified a unique identifier that I could quickly query in Silk. So you can see there are all the 85 variants. So I did my handy dandy RW stats query, probably the only one I know off by heart. And it identified 22 of the 85 Ghost variants. And so I now only have about 140,000 unidentified flow records. The top variant we have there was 9969, which turned out to be PCRAT. We had 52,000 flows that had that PCRAT string in there. So I still wasn't happy with that. I was like, there's got to be more types of ghosts in there, but why aren't they identified? What do they look like? Are they different signatures? Do they use different magic words? So I was curious. I needed to find out. So enter SuperMediator. So SuperMediator is an IPFix mediator. It takes any IPFix information element that YAF can export. It can export to multiple collectors, so one being Silk, and then it can also just write text files, CSV files, and you can use Unix tools to kind of grep through those. You can also import it into like a MySQL database if you prefer to do something like that. The next version, you can have multiple collectors, but that one's not released on our public site yet. So how did I configure SuperMediator? Well, you can write out exactly which fields you want in the text files. So I did application label first, and that way that could just allow me to bin, okay, what are all the 9,000s? What are all the known Ghost variants? what are all the unidentified stuff, and see if I can find any patterns in that in the flow data. And of course, you can do this in Silk, but the thing that you can't do in Silk was the particular flow stats I was looking at, the advanced, what I call advanced flow statistics, which Silk doesn't collect. So that's mostly in the right column. Bytes and reverse bytes, obviously Silk collects that information, but what you might not be familiar with are things called data, what I call data bytes, which are just the bytes transferred in the payload of the flow. Reverse data bytes, obviously, in the other direction. Small packets are the number of packets in the flow that had less than 60 bytes. Large packets are the number of packets in the flow that had more than 220 bytes. The number of non-empty packets, so packets that carried a payload. The maximum size of the packet in the flow. And then the last one is the first 8, the directionality of the first 8 non-empty packets. So a 0 in the forward direction and 1 in the reverse direction, which kind of came in handy. So my supermediator results, if I quickly binned all the 9,000 flows, I got 60,000 biflows that were identified as ghosts, and I had 86,000 unidentified. So this is just a quick screenshot, if I could get this to work here, okay, of the 9,000s, so the stuff that was identified as ghost. And you can quickly see here, your TCP flags, pretty obvious. The next row here was packets and reverse packets, so all in the same range. Then we have bytes and reverse bytes, so all in the 300 to 400 level. And then we had payload bytes, which you can see payload bytes always seem to match reverse payload bytes. So that was kind of interesting. Small packets, large packets, nothing really interesting there. They all seem to have one non-empty packet in each direction. Max size, and that obviously corresponds to max size equals reverse max size because they only had one packet that carried a payload in the flow. And then directionality, they all had basically 1 in each direction, so 0, 2. So cool, so now I have a pattern. So maybe I can apply that to all of the unidentified flows and see what else pops out. And what I did here was I removed all the unwanted flows from the unidentified flows. And what I mean by unwanted flows are any flows with the source or destination port of 138, 139. I was using YAF 2.6 for this, and we didn't have an application label for 139, which is the NetBIOS datagram service. So none of those were labeled as 139. And in YAF 2.7, we do have one for that. I removed any flows with a data byte count of 0. So it didn't really, there was no packets in the flow that carried a payload. So I took those out. And then I found flows with a pattern that had no more than one small packet in the forward direction, 0 in the other direction. It had at least one non-empty packet in either direction. The max packet size equals the reverse max packet size, and then the directionality always equal 2. So what were my results here? So I ended up removing 44,000 biflows using the top little piece there, all the 138, 139 stuff. Ghost actually affects Windows machines, so kind of made sense. 37,500 biflows followed that second list of bullets with that pattern. So why weren't they identified with the Norman ASA ghost variants? Are they using different signatures? What's the deal here? So I pulled out one of the PCAPs that weren't identified as ghost. And this is what I found. So I opened this up in Wireshark, and as you can see, this isn't working. Oh, here we go. 4 bytes here, and if you switch the byte order here, was hex 101, which actually turns out to be 257. Half of 544 is 257. So that made sense. So that was probably the compressed length of the packet. 3801, well, that could definitely be the uncompressed length. And then you'll see here FWKJG. I said, okay, well, that seems like one of the magic words that Actually, that is one of the magic words that is identified in the Norman report. It's just not at the right offset. It's not at the beginning. It's after the 2 lengths. And then you also see the zlib header right here. I said, okay, well, this bad guy, instead of just changing the 5-byte magic word, he moved things around a little bit to try to not be detected. So I said, okay, how many more were like this? So I didn't want to go through all of those PCAP files, open every single one up in Wireshark, and identify what was the magic word. So I ran all the unidentified PCAP files through YAF again, and I exported the first 100 bytes of payload because that's all I was really interested in. And I was only interested in the first like 20 bytes, but I did the first 100 just to make sure that there wasn't any signatures I could identify that were past the first 20 bytes. And this is what I found. So this flow was similar to the one I just showed you with the FWKJG, but it didn't have the zlib header. This one, the one below that, it was a little bit different where the first 4 bytes, if you reverse the byte order, it's FF, which is 256, which was the length of the packet, and then it had the 5-byte word here, which I had to blur out because that wasn't one of the ones identified in the Norman ASA report. And then it had the uncompressed length, and it also didn't have a zlib header. So I said, oh, okay, that's a different one. So I ended up just being able to like run through these text files and pick out all the different variants and all the different signatures that, that Ghost was using. So my results, I identified several signature variants of Ghost. I found 55 new magic words. And ultimately, I said, I can identify this in YAF with an application label now. It's pretty easy to identify now that I know all the different signatures, or at least the ones that we have samples for. And I wrote an application label, which was in the YAF 2.7 version that I released last week, which correctly identified 97% of all the Ghost traffic that we have. There was a few different variants that I know that are Ghosts, but they would result in too many false positives if they didn't follow any particular pattern. And then also, because I collected all the deep packet inspection data, so all the DNS queries and responses, I could correlate over 3,000 unique domain names with Ghost variants. So I noticed that PCRAT, for example, used one particular domain a lot, so I could quickly make that table. So just to be clear, there's a disclaimer, not all Ghost traffic is going to follow that little algorithm I gave you. Because of the way it's run in our lab, this was really just looking at the login command that Ghost does. So the server, which is the infected machine, logs into the client, which is the C2, and says, hey, I'm here, and the client adds that to the list. And then the server should really wait for actual commands and then respond from the client with whatever the client's requesting. So with real Ghost traffic that's actually sending commands and responses, you might actually see the client have a lot of small packets, because all it really is sending the server, which is the infected machine, is a command code, which is really just 1 byte. So you should really see just a lot of small packets, and then the server responding with a lot of large packets. So, but we can always identify Ghosts based on the first 13 bytes that are sent in the clear. So how does this relate to PCAP analysis, right? I just showed you a bunch of flow analysis. So what I wanted to show you is how would I now search for Ghosts in a large pile of PCAP? So at the time I was writing this, the DEFCON capture the flag PCAP data was made available. There's 409 gigs of data, and it was separated by team and day. So I ran YAF and Silk and SuperMeteor just like I did at the beginning, but now with my new Ghost application label. And I wanted to see if there was any Ghost traffic in that data. And what came out of it, with my handy dandy Silk query, the one and only one I know, was 9997 is what I used as my application label for Ghost, and I saw 38 flows identified as ghosts. And I said, that's a little weird because that's not a lot, and I would expect more if somebody was using ghosts in the DEFCON data. So let's go look at that data, right? So this is where I actually show you how to use the PCAP analysis tools in YAF. And so what I did was, I used RW filter on the application label 9997, which was ghost, and I piped that to RW silk to IP fix, which takes silk data and converts it to IP fix, and then I piped that to a tool called get flow key hash that comes with YAF, which calculates that flow key hash based on the 5 tuple and the VLAN, and then it calculates the start time in milliseconds. So these are all the flows that were identified as ghost. And so now I can pipe that right to YAF metadata PCAP, which takes all of the DEFCON data, the 409 gigs, and the PCAP meta file, which I talked about in the beginning, that indexes that PCAP data, the flow key hash and the start time. And what it writes is a PCAP file for the flow that you're looking for. So you can see this example. This was the first flow in that list. And you can see here it says in the first 4 bytes, DMDT. And if I would have shown the hex here, the next 4 bytes would have been the uncompressed packet size, and then the following 4 bytes would have been something that could have been the uncompressed packet length, but no zlib header. And I said, well, that's kind of weird. It's usually 5 bytes. And then this seems a little bit small for Ghost, 99 bytes. So I wonder if any other, and most of the ones that were identified as Ghost either had a string called or a string that said DMDT or a string that said ELIZA. And I said, I wonder if any other packets in the flow had those strings in them. So I ran YAF again over all the DEFCON data, and I used DMDT and ELIZA as signatures, which just runs it as a regular expression over the payload. And what I found was 6666 was ELIZA, and there was almost 8 million flows that had that in the payload. And I said, okay, this isn't Ghost then. And it turned out when I Googled ELIZA and DEFCON, it was one of the capture the flag challenges at DEFCON, so that's why there was so much data in there. And then 8888 was DMDT, and 80% of the DMDT traffic went to the last place team. And so I decided that that's not Ghost. It might have been one of the vulnerability in one of the services that they had to run, but it definitely wasn't Ghost. So the result here was that that was probably some false positives, but I could quickly go back into the PCAPs and really find that out. And then I changed the application label in YAF to not be so loose with the restrictions on the 5-byte signature. So last but not least, what am I trying to show you? A lot of the times when I'm doing any kind of analysis, I'm running a lot of PCAP data through YAF, and I'm trying to make sure that YAF's doing the right thing and producing the output that I expect it to produce. And sometimes I go and I look at the flow data and I'm like, that flow looks a little weird. I'm like, is that really how it was in the PCAP? And I feel like a lot of times in organizations, you get to that point where you have a weird flow and you're like, I'd really like to get to the ground truth and see what actually happened. So I need to go back and look at the PCAP data. So I could never find a tool that would be able to do this for me, and so I wrote some. So TCP dump, it's hard to do with just TCP dump. You have to determine which PCAPs contain your flow. You can't run multiple PCAPs through TCP dump. So you have to use something like merge-cap to merge the PCAP file. So now you have even bigger PCAP file. And then you have to write a great BPF filter to return that one particular flow that you're looking for. And I don't know about you, but every time I write a BPF filter, I have to go into the TCP dump man page. It takes me about 5 minutes to figure out exactly which one I want. And maybe it'll return only one session. If it returns more than one, I have to go back and separate the flows up. So with YAF, once you have the flow data, once you have indexed all the PCAP data, it's one step. You run YAF metadata PCAP, and it generates the particular PCAP that you're looking for. In 1.7 terabytes of PCAP data, I can return the PCAP that you're looking for in under a second. TCP dump, it's about a minute if you write the most awesome BPF filter that you can write. So I hope that this was helpful. I hope that you can make use of this. And any questions? Hopefully I didn't run over too much. Okay. Oh. And if you have any questions later, catch me afterwards, or you can always email our Net to Help mailing address if you're looking for support or have a question on any of the tools I discussed. I glanced over a lot of the details of how to run them, so if you need help doing that, feel free to email Net to Help. It comes to me or one of the other developers that can answer the question.